Okay, so in these notes right here, we're going to be talking about perpendicular bisector and some theorem type stuff. All right, so looking at this, which one does not belong? All right, and I know that there can be different perspectives, but let's just start talking about things. All right, now, first off, let's just make these lines just for this one. We don't need to really talk about in all of them, but this right here, boom, remember that means right angle, which are 90 degrees. All right, and then for an abundant amount of reasons, you can say, well, we got vertical angles right here, so that is also 90 degrees. Then you can say, well, we have, this is stuff we're going to be talking about too, kind of the next problem. This is a guaranteed linear pair right here, which must be supplementary. All right, since that's 90, this also must be 90 degrees. I can even write this over here, 90 degrees. And then we got some vertical angle action going over here, 90 degrees. All right, so this will be fun for later, but two lines that intersect form four right angles. Okay, so that was B. Pretty cool stuff right here. Okay, now over here, I said I wasn't going to do it, but I lied, I changed my mind. Okay, we got two lines intersecting, and these two angles are congruent. All right, so I didn't dabble too much into it last time, but let's dabble it into this time. We have a linear pair, which is supplementary. Okay, then I'm just going to set up a pretty cool equation. I'm going to say, well, this is x and this is x. All right, supplementary is a fancy word of saying two angles add up to 180 degrees. All right, so then you would get 2x equals 180, or x would be 90 degrees. All righty, so that's 90 degrees, that's 90 degrees. Then vertical angles or more linear pairs, however you want to see it, boom, we got 90 degree angles going on again. Okay. Oh, two lines that intersect. Oh my gosh, guys, I'm glad I could rewind. Two lines that intersect perpendicular. Two lines that intersect perpendicular form four right angles. Ooh, that would have been a major typo. Let's go back here and reiterate it. Two lines that form, we'll write the converse of this, we'll write it backwards, form four right angles are perpendicular. Okay, we can't forget that word perpendicular. I can't believe I forgot it. Whew. I'm sweating over here now. Because then this over here, again, you guys do a good job of asking questions. You say, what does this mean? Well, it's just time we know it now. I've said it a lot. We got to store it into our brains. It's perpendicular. All right, so based off these two facts I wrote here, these are two lines that intersecting. They're perpendicular, right angle, right angle, right angle, right angle, 90 degrees, 90 degrees, 90 degrees, 90 degrees. All right, boom. Notice that we just got right angles and 90 degrees all over the place. Cool, and this one, and this one, and this one. This one, they're just intersecting. All right, they're two lines intersecting at a single point. All right, intersecting does not imply perpendicular. Now, in truthfulness, they do look perpendicular, but it doesn't mean that they are perpendicular. All right, what's this angle measure? Could be 89.9 degrees. All right, and then we'll do like the shrugging emoji. Like, we don't know. What could it be? We just don't know. Okay? So which one doesn't belong, in my opinion? A. I know you could make valid arguments for other ones, but that's the one I'm sticking with. All right? Theorem. All right? Theorem. All right? We're going to freestyle this theorem. It's going to be so much fun. If a point C is the same distance as A as it is from B, then C must be on the perpendicular bisector of AB. All right, so let's just go ahead and I'm going to draw a random line AB. All right. Now, anywhere on this line, it's fair to say that there's going to be a midpoint. All right, I did my best, but let's just go ahead and say that that's a midpoint. All right, not on this line, we got some random point C. All right, now it's not entirely random because it's saying it does lie equidistant from C or A and B. All right, so we got some random segment AB. I found a midpoint just for fun. I'm allowed to do that. I'm allowed to have fun doing math. Anywhere on this, or excuse me, C is not on the line, but is equidistant from A to B. Now, what we have to prove is that it lies on the perpendicular bisector. All right? So I guess step 1, draw AB and label midpoint. Okay. Step 2, draw point C and show it is equidistant to A and B. Okay. Now, I'm just going to connect C and M for fun. All right, now I have two triangles. All right. So I guess step 3, connect CM. And now we're going to talk about things. All right. Again, we're just kind of freestyling this. Next CM, comma, CM is congruent to CM by the reflexive property. Okay. Let's rewind a little bit. I could have done this up here. When I drew the midpoint, AM is congruent to MB. All right, just because it was the midpoint. All right, and we're just allowed to find the midpoint of any lines that we want. Over here, just some given information was CA was congruent to CB. That was given information. All right. So now we do have a lot going on. We have AMC congruent to triangle M or BMC. Okay, these are two triangles. Okay, they are congruent by side. All right. We have all corresponding sides, all right? We have the midpoints, we have the given ones, we have the reflexive. We know the triangles are congruent. All right? Since we know that the triangles are congruent, all right, I guess that could be step 4, and I kind of put that underlined because it brings us to our next phase. I'll underline that, is we're gonna start picking off some things, all right? That means that angle AMB AMC is congruent to angle BMC. All right? Those two angles must be congruent. Okay? Because the triangles are congruent. Remember, that means the corresponding parts are congruent. All right? Then I'm going to be very free flow in this. AMC plus BMC, these angles, we're not going to go too crazy. I can make this really long because they're a linear pair. Okay, they're congruent angles that form a linear pair. So it's going to just kind of be like we were talking about above, and this one right here. We're going to be kind of using the same logic where we can say, thus, both angles 90 degrees. All right. We said that they're congruent. They form a linear pair that must be 90 degrees. All right. So this is specifically going to say, well, the lines are perpendicular. Thus, AB perpendicular to MC. All right, so the overall punchline, all right, CM bisects AB. We showed that by just simply drawing it to the midpoint. And then AB is perpendicular to CM. So point C is on the perpendicular bisector. Okay? This was incredibly dense and tough, all right? This is a dense, tough, hard, all right? As we see though, we'll just boil it down to stuff like we had a midpoint, all right? It told us this information. We can figure this out hopefully with low-level logic, all right? These are a lot of simple steps put together, which makes it hard, all right? But then we can say that the triangles are congruent. So corresponding parts are congruent. There's a linear pair with congruent angles. So that means everything's 90 degrees. That means that it's a perpendicular bisector, all right? That's a lot, all right? But if you look at each individual step, hopefully it's not too tough, all right? So this next part is going to be kind of the same exact thing. We're just going to go in reverse, all right? Now we're given QR is the perpendicular bisector of ST. So this perpendicular part's already marked, but it also means that, okay? We're going to prove that triangle QSR and QTR are congruent, okay? So we can kind of free flow, but I just kind of like to label my steps. All right, given QR perpendicular bisector of ST, okay, we know specifically SR is congruent to RT because the midpoint, all right, bisector, midpoint, those are somewhat interchangeable, and angle SRQ is congruent to angle TRQ. Okay, it's the bisector. Okay, we're going to say both right angles. Right angles are congruent to each other. Okay. Next, reflexive property. So we were just given information. Basically, if you know the definition of angle bisector or perpendicular bisector, you have a side and an angle, And then if you can just simply say QR is congruent to QR because of the reflexive property, okay, we have a side, angle, side. So we can say in step 3, the triangles are congruent. QSR is congruent to triangle QTR by side, angle, side. Sweet. Okay. So those are kind of the same problems going in different orders, but the logic is very intertwined. Now we got just some repetition stuff right here. In the figure, point F is the midpoint that was given to us of GE. What additional information do you need to show that the triangle DEF is congruent to HGF by side, angle, side? Okay, so we have a side, okay, we need an angle and another side. All right, now we do have this parallel lines, and we could use alternate interior angles, but I don't even have to worry about that when we see the bow tie or any of this. I would rather just go right here. I'm a big vertical angles fan. All right, it doesn't matter if the lines are parallel or this or that. When we have angles formed by an X, we have vertical angles. All right, so we have angle DFE is congruent to angle HFG, vertical angles. Okay, so basically now we just need one more side. We have a side. The definition of midpoint was given to us. All right, I guess I could have wrote that out. I can say GF is congruent to EF, midpoint stuff. Then we have the vertical angles. The last piece of information I would need is to say DF and FG, right? DF is congruent to FH, excuse me. This is what we would need to know because we have a side included angle and then another side. All right, so that's what we would need to know for side, angle, side. And then last problem on this page, it says prove triangles MJK is congruent to KLM. All right, boom. All right, step 1, before I even get too involved in the picture, MK is congruent to MK. All right, so I have a side for both of the triangles. Okay. Now you can call it the Z angle, or it could be other things you call it. It's not always a Z, but in this case it's Z. All right. We have the alternate interior angles right here. All right, these lines are parallel. When alternate interior angles are formed by parallel lines, they are congruent. All right, so this would be specifically JKM is congruent to MLK, or LMK, angle by alternate interior angles. Okay. Now here, it's because these lines are parallel as well. We have parallel lines cut by a transversal. And remember, a lot of times when we see parallel lines, not all the times, but a lot of times, we're going to be having some kind of alternate interior angles. JMK, L angle LKM, those are also by alternate interior angles. Okay, so we do have an angle, side, and then an angle. All right, this is an included side All right, it's between the angles. All right, it's formed by them between them. So that's one way, basically the only way we could prove that these two triangles are congruent. All right, by angle, side, angle. All right, and just a little recap. I think these notes were a little tedious. I don't know how to spell tedious. Confusing. Heavy logic. Okay. We will do stuff like this throughout the year. We will get better. All right, don't be too concerned. All right, this is dense stuff. All right, kind of proving stuff. We haven't practiced it too much yet. All right, but just looking at spatial relationships, using stuff we know, putting it all together, it's a skill set we'll practice, and don't worry.